Let us assume that this is the situation just before the RF pulse is switched off. When the RF pulse is switched off, the protons get out of step, out of phase again, as nobody is telling them to stay in step. For the sake of simplicity, this has been illustrated for a group of protons which all point up. Let us have a look at what happens one more time. Before the RF pulse is switched off, a transversal magnetization has been established. When the RF pulse is switched off, the protons get out of step, fan out. Thus, the transversal magnetization decreases. When you look at these dephasing proton ensembles from the top, it becomes obvious how they fan out. Being in phase in the first place, then losing phase coherence, pointing less and less in the same direction. We heard earlier that protons precess with a frequency which is determined by the magnetic field strength that they are in. And all the protons should experience the same magnetic field. This, however, is not the case. Firstly, the field of the MR magnet in which the patient is placed is not totally uniform, not totally homogeneous, but varies a little, thus causing different precession frequencies. And, secondly, each proton is influenced by the small magnetic fields from neighboring nuclei that are also not distributed evenly, thus causing different precession frequencies too. These internal magnetic field variations are somehow characteristic of a tissue. Now, let us return to our previous illustration. After the RF pulse is switched off, the protons are no longer forced to stay in step. And as they have different precession frequencies, as we've just learned, they'll soon be out of phase. It is interesting to see how fast the protons get out of phase. Just suppose that one proton, P1, is rotating at 10 million revolutions per second. In other words, with a precessing frequency of 10 megahertz. Due to inhomogeneities, a neighboring proton, P2, is in a magnetic field which is 1% stronger. This proton has a precession frequency of 10.1 megahertz, 1% more. In 5 microseconds, P2 will have made 50.5 turns or revolutions, while proton P1 will have made only 50. So, in this short time span, the protons will be 180 degrees out of phase, cancelling their magnetic moments in the respective plane. Similar to what we did for the longitudinal magnetization, we can plot transversal magnetization versus time. What we get is a curve like this one. This curve is going downhill, as transversal magnetization disappears with time. And as you probably expect, there is also a time constant, describing how fast transversal magnetization vanishes, goes downhill. This time constant is the transversal relaxation time, T2. How to remember what T2 is? Easy. T2 is T times 2 is double T is TT. And this means it describes the T transversal, thus the relaxation of the transversal magnetization. The resulting curve is thus called a T2 curve. Another term for transversal relaxation is spin-spin relaxation. reminding us of the underlying mechanism, a spin-spin interaction. How to remember which one is the T1 and which one the T2 curve? Just put both curves together. You can see something like a mountain with a ski slope. You first have to climb to the top, T1 curve, before you can ski down, T2 curve. It takes longer to climb a mountain than to ski down, which helps us to remember that T1 is normally longer than T2. So, time for a review.